look at the unit circle and circular function. Now, suppose we have a circle centered at the origin that has a radius of 1. Let's look at this arc length S. Okay, we have the arc length S, we have the angle theta. Remember we had S is equal to R theta, but when R is 1, okay, we have S is equal to theta. So in our trig functions, we can make the substitution that theta is equal to S. And we're going to do that to rewrite our trig functions on the unit circle in terms of the arc length S instead of necessarily theta. So x is equal to cosine of S and y is equal to sine of S. Now, these are equivalent to x, in this case, is cosine of theta, and y is sine of theta. But again, because r is 1, s is numerically equal to s. And so on the unit circle, we have x squared plus y squared is 1. We have key points we're always going to pay attention to. 0, 1, 1, 0, 0, 1, negative 1, 0, and 0, negative 1. They're going to be very helpful milestones in what we're doing. When interpreted this way, we call these circular functions because they're represented on the circle. Now, for any real number, f represented by a directed arc on the unit circle, sine of s is equal to y, cosine of s is equal to s, tan of s is equal to y over x, and we can't let x equal to 0. Cosecant of s is 1 over y, and y cannot equal 0. Secant of s is 1 over x, where x is not 0. And cotangent of s is x over y, where y does not equal 0. Now we can use this 1 here because remember this is equal to the radius. Now here's your basic unit circle. You need to memorize this, and you need to know that 210 degrees corresponds to 7 pi over 6, and that corresponds to the point negative square root of 3 over 2, comma, minus 1/2. You need to know this for all of the principal angles. Now, if you notice, there's a lot of symmetry here. So you really have to memorize the first quadrant, 0, 30, 45, 60, and 90, and then look at symmetry to find the values in the second, third, and fourth quadrant. So the unit circle has symmetry with respect to both the x-axis, the y-axis, and the origin. I guess all three of those. If the point AB is on the unit circle, so is A minus B, minus AB, and minus A minus B. For a point on the unit circle, the reference arc is the shortest arc from the point itself to the nearest point on the x-axis. So, in quadrant 1, the real number pi over 3 is associated with the point 1/2 square root of 3 over 2 on the unit circle. So, this is my S here, pi over 3, and when it's in the first quadrant. It corresponds to the point 1/2 square root of 3 over 2. The cosine of this S is 1/2, and the sine is the y value, or square root of 3 over 2. In the second quadrant, it occurs at 2 pi over 3, and it has y-axis symmetry. Now, the x value is negative because it is in the second quadrant. The y value is the same. So the cosine is negative 1/2, while the sine is still square root of 3 over 2. In the third quadrant, that's the same thing as pi plus pi over 3, or 4 pi over 3. It has origin symmetry. And so the 1/2 becomes minus 1/2. Square root of 3 over 2 becomes minus square root of 3 over 2. The cosine is minus 1/2. So the cosine of 4 pi over 3 is minus 1/2, while the sine of 4 pi over 3 is minus square root of 3 over 2. And in the fourth quadrant, that's 2 pi minus pi over 3, or 5 pi over 3. It has an x-axis symmetry. And so it corresponds to the point 1/2 minus square root of 3 over 2. And the cosine of 5 pi over 3 is 1/2, while the sine of 5 pi over 3 is minus the square root of 3 over 2. Now, because cosine of s is equal to x and sine of s is equal to y, we can replace these in the unit circle x squared plus y squared equal to 1 to get cosine squared of s plus sine squared of s is equal to 1. The domain of the sine and cosine is all real numbers. Any number can be substituted into a sine or cosine, and you'll get a solution. The tangent has a domain. Remember, these are the inputs of f such that s cannot equal 2n plus 1 times pi over 2, where n is any integer. While the cotangent and cosecant are the set of s such that s cannot equal n pi, where n is any integer. So this would be pi, 2 pi, 3 pi, or even negative 3 pi, negative 2 pi. Now, circular function values of real numbers are obtained in the same way as the trig functions, values of angles measured in radians. This applies to finding exact values, such as reference angles, and calculator approximations. But again, put your calculator in radian mode when finding circular function values. If I wanted to find the exact value of sine of 3 pi over 2, cosine 3 pi over 2, and tan 3 pi over 2, I would evaluate the circular function at the real number 3 pi over 2. And that's the same thing as evaluating it at 3 pi over 2 radians. Now, at 3 pi over 2 radians, it intersects the unit circle at 0, negative 1. That's my x value, and that's my y value. So, since sine of s is equal to y, cosine of s is equal to x, and tangent of s is equal to y over x, I see that the sine of 3 pi over 2 is equal to y, which is negative 1. Cosine of 3 pi over 2 is equal to x, which is 0. And the tangent is undefined because I cannot have 0 in the denominator. Now let's use the functions to find the exact value of cosine of 7 pi over 4 and sine of 7 pi over 4. So let's find 7 pi over 4. Where is it? It's right here. Here's 7 pi over 4. And that corresponds to the point square root of 2 over 2 minus square root of 2 over 2. And so the cosine of 7 pi over 4 is equal to the square root of 2 over 2, while the sine of 7 pi over 4 corresponds to minus square root of 2 over 2. Now, let's use this figure to determine the tangent of minus 5 pi over 3. So minus 5 pi over 3 means we're going to go back, all right? So when we go back, we're going to go back pi over 3 units. So we're going to go back 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3. That brings me to this point right here, pi over 3. It has x value of 1/2, y value of root 3 over 2. So minus 5 pi over 3 corresponds to, right here, 60 degrees. So the tangent of theta is y over x. So the tangent of minus 5 pi over 3 is the same as the tangent of pi over 3, which is square root of 3 over 2, divided by 1/2, or square root of 3. Use reference angles in and radian to degree conversions to find the exact value of cosine 2 pi over 3. I know 2 pi over 3 corresponds to an angle of 120. In standard position, 120 is in the second quadrant and has a reference angle of 60 degrees. So the cosine of 2 pi over 3 is the same as the cosine of 120, which is minus the cosine of 60, which is minus 1/2. This negative sign because cosine is negative in the second quadrant. You also could have referenced the memorized unit circle. Find approximate values. Cosine of 185. Again, there's no unit given, so we're going to assume it's radians. This has to be done on a calculator. That gives us a value of minus 0.2755, and the cosine of 0.5149 is about 0.8703. Tangent of 1.309, we want to find 1 over the tangent of 1.3209, or 0.2552. Secant, now without the parentheses, they're really there, of minus 2.9234, we want to do 1 over cosine of minus 2.9234, and we get negative 1.0243. The mistake you're going to make is having it in degrees when it should be in radian mode. Remember, if you're finding a circular function value of a real number, it has to be in radians. Let's approximate the value of s in the interval 0 pi over 2 if cosine of s is 90.9685. 0 to pi over 2 is first quadrant. So we're going to use the inverse cosine on our calculator to get 0.2517. Find the exact value of s in the interval of 3 pi over 2. Now this is quadrant 3 if tangent of s is 1. Now we know tangent of pi over 4 is 1, and in quadrant 3, tangent is positive. So the angle whose tangent is 1 is 0.7853. Now, we're in the third quadrant, all right, so we're going to need to add pi to it. So s becomes 5 pi over 4. Because I know that tangent of 5 pi over 4 is also 1. You do not have to memorize this equation. Suppose I give you the angle of elevation of the sun in the sky at a latitude L, and the sine of theta is cosine of d, cosine of L, cosine omega, plus sine of d, sine of L, where theta equals 0 is sunrise, and theta equals pi over 2 is when the sun is directly overhead. Omega is the number of radians that the Earth has rotated through since noon, when omega was 0. And d is the declination of the sun, and that varies because the Earth is tilted on its axis. Please notice I'm going to give you everything you need in this equation. Sacramento, California has an L of 38.5 or 0.6720 radians. Find the angle of elevation theta of the sun at 3 p.m. on February 29, 2012, where at that time t is minus 0.1425 and omega is about 0.7854. Now, let's pull out that ugly formula and simply substitute in. You should get the sine of theta is about 0.459. Now, in order to get the answer, okay, sine of theta is 0.459. So we take the arc sine, and we get that the angle is 0.444773 radians. All right, so this gives me the radians answer. degrees, I multiply by 180 divided by pi, or 27.34 degrees. Now we can express functions as values of lengths of line segments. This diagram gives a correspondence that ties all of the triangle ratios to a square and the unit circle. Now, if you look at each one of these and analyze them, P is at a radius of 1, and it corresponds to xy, or cosine theta, sine theta. R is where it hits the x-axis, and S is where it hits the y-axis. T completes out our unit square, and U is where the ray that goes through the origin through P intersects the horizontal line here. Now, for cosine and sine, we can use the triangle POQ, okay, and the regular ratios that we've been using. So cosine of theta corresponds to OQ, or this horizontal segment, while the sine of theta corresponds to PQ, this vertical segment. We've been doing this. For tangent, we need to use the right triangle VOR. Big one, it starts here, VOR. And look at those right triangle ratios. And we see that the tangent of theta corresponds to the segment VR. So this is vertical segment right here. All right. Well, the secant of theta corresponds to OB. Trouble with my marker here. This is my OB, so that corresponds to the secant. Now, for cosecant and cotangent, first you have to realize that US and OR are parallel. So SUO is equal to theta because they're alternate interior angles to POQ. So we can use the right triangle USO and the right triangle ratios. So cosecant SUO corresponds to cosecant of theta, and that corresponds to OU. All right, here it is. While cotangent corresponds to cotangent of SUO corresponds to cotangent of theta, and that corresponds to US. This is a very nice summary. I want you to study it, the corresponding lengths of the segments and how they relate to the trig functions. Now, suppose that you have an angle TVU and it measures 60 degrees. Find the exact segments of all of these segments. Well, let's just get started. Angle TVU has the same measure as OVR because they're vertical angles. All right, so these two are the same. Therefore, OVR is 60 degrees. Now, because it's one of the acute angles of a right angle, that means theta has to be 30 degrees. Since theta is 30, all right, that tells me OQ is cosine of 30, or root 3 over 2. PQ is sine of 30, or 1/2. VR is tan of 30, or root 3 over 3. OB is secant of 30, 2 root 3 over 2. 2 root 3 over 3, excuse me. And OU is cosecant of 30, or equal to